Thank you very much. Good afternoon, everybody. Okay, let's continue our discussion from last time. We have reached the last set of charts, finally. The last set of charts. But this one is a big one. So we need to understand how it works. And this is in regarding to the what? To the oscillators, the RF oscillators, and the phase lock loop-based frequency synthesizers. Clear? First of all, we need to understand also the difference between an oscillator and a synthesizer, and so on and so forth. I was hoping for 5 lectures on this. We ended up with only 4 lectures. We have 4 more lectures to go. So we will see what we are going to be covering. So what we are going to be covering, the outline of this set of charts, is first of all the approaches to oscillators. How do we design the oscillator? We will see that there are 2 different types of what, or 2 approaches to designing an oscillator. The first one is called the what? A feedback approach. And the second one is called the what? A negative resistance approach. This one looks weird. What does negative resistance mean? We'll get to that in a minute. We will look at different types of what oscillators. Most widely used of them is what is known as what? The Colptist oscillator. We will look at a highly stable types of oscillator. We call them what? The crystal oscillators, which are usually used as what? Reference oscillators. We will look at what? VCOs. VCO stands for what? A voltage controlled oscillator. We will look at the basics of phase lock loops. This one, by the way, is a course by itself. In other words, the entire semester could be dedicated to what? To phase lock loop. We will dedicate only what? 1 lecture on it. We try to what? Understand it very quickly. Then we will look at what? We will look at different types of what? The frequency synthesizers that are based on the phase lock loop. And we will also be looking at what is known as direct digital synthesizer. Direct digital synthesizer in digital domain rather than in the what? In the analog domain. And my feeling is that we'll cover the whole thing. And the question is what? I would like some more details into each one of them. But unfortunately, we will not be able to do it. This class, again, as I told you, cannot be covered with too much detail in 1 semester. It cannot. It's a huge topic. So we try our best to learn as much as possible. Oh, first of all, let's understand what do I mean by an oscillator. Question number 1. Do we denote an oscillator at the receiver or both at the transmitter and the receiver? Both at the transmitter and the receiver. An oscillator is an autonomous system. Let's stop here for just a second. Or an autonomous device. What does an autonomous device mean? It means it does not have an input. Just like the what? If you see in the diagram, how would you sketch this? Look at this. This is the mux. I'm sorry. This is the what? The mixer. Did you get this? Well, it's the same as it sounds like a mux, but it's not. It's a mixer. Does it have inputs? It has input. This is an input. This is an input. This is the LO. What do you have in the LO? The LO, you write what? OSC. What is OSC? Oscillator. Does it have an input? No input. An oscillator is unlike the what? Amplifier. In an amplifier, it has an input and a what? Output. An oscillator is a what? Is an autonomous system. It builds the oscillation by itself. Now, you might say, how does it build the oscillation by itself? Something triggers it. Maybe just what? Internal noise, and some fluctuations from a power supply, and so on and so forth. It starts with the what? A certain what? A certain fluctuations. You follow me or not? But then it needs to what? Build it up. How would it build it up? It build it up through the use of a what? An amplifier. Do you understand that or not? Which means what? What is the point that I'm trying to make? The point that I'm trying to make is that an oscillator cannot be designed as a passive circuit. It must have a what? An amplification in the circuit to what? To build this oscillation until you reach the what? The right amplitude, and then it will need to what? Sustain it. Did you get my point or not? So an oscillator always involves, the design of an oscillator always involves the what? An amplifier. An amplifier is part of the design of what? Of the oscillator. Did you get this or not? The amplifier will build the what? Will build the amplitude. But the question is what? Who will set the frequency? When you need to set the frequency, part of the oscillator needs to have a what? A tank circuit. A tank circuit. See, if you do have a tank circuit, let's assume that we do have a parallel tank circuit. Is this a tank circuit? That's a tank circuit. LC. Assume it's ideal. Assume it's ideal. Yes? Will it oscillate? It will oscillate. What is the frequency? What is the fundamental frequency? The fundamental frequency is 1 over what? Square root of LC. But will it sustain it? It will not sustain it. Why? Because these are not what? Ideal components. There are what? There are a resistive element in them, and with the passage of time, these resistance will what? Will die down. Did you follow me or not? Through experimentation, this is what they said. Listen to this. For a tank circuit operating at, let's say, F naught. Let's assume, just for sake of argument, 1 gigahertz. 1 gigahertz. If the Q, what is the Q? The quality factor of this tank circuit. If the Q, remember, by the way, if there is no R in there, the Q is what? If there is no R, do you remember the Q? What is the Q? Definition of the Q is omega naught L over what? R, or 1 over omega naught. Where is the R? Here, where is the R? If there is no R, what is the Q? Infinity. And they tell you the oscillator will sustain its oscillation for roughly 20 to 25, roughly for what? Q cycles. Q cycles. I want you to understand what you mean by Q cycles. Let's assume it's 1 gigahertz. Yes? 1 gigahertz. What is the period? What is the period of this guy? Period of one cycle is what? 1 nanosecond. You agree? Let's assume the Q is 100. What does this tell you? What does it tell you? It tells you that this, if Q is equal to what? 100, then the oscillator will sustain its oscillation for how long? For 100 nanoseconds. High or low? Then what began? It began to what? It began to go down the drain. Did you understand what I just said? Oh, no. By the way, even if you say 100 is small, let's assume the Q is what? 1 million. Yes? Which is what? 10 to the what? 6. How many will it be? It will sustain it for only what? 1 millisecond. And then what happens after that? It dies. Yes or no? Do we need an amplifier? What do we need the amplifier for? We need the amplifier to what? Sustain that oscillation. To what? To put energy back, to recover from the energy lost in the what? In the resistance. Did you understand that or not? The resistor is going to what? Loses energy, dissipate power. We need to what? Replace that. How do I replace that? I replace that only by using a what? An amplifier. Clear? Yes or no? Okay, so I will get to the detail in just a second. The oscillator is a device. There is no input. Now, if there is no input, where is the output? Where is the power at the output coming from? The power at the output must be coming from what? From a DC. Do you understand that or not? By the way, let's see if you remember this definition. Efficiency equal to what? The R of power over what? DC power. Have we seen this definition before? With who? With amplifier. With power amplifier. It's the same definition. But the difference is what? In power amplifier, we also has an input what? An input R of power, even though it's small, but there is an input R of power. In here, there is no R of input power, which means what? We are just converting the DC to what? To the AC power. Did you get it or not? We are converting, the DC power to the what? To the R of power. Clear? Okay. Now, an oscillator. Listen to me. An oscillator. Does it generate sine wave, or does it generate square wave, or does it generate sawtooth or whatever, or it doesn't matter? There are many types of oscillators. There are sinusoidal oscillators that generate what? Sine wave. Now, when you generate sine wave, what are you generating? A single frequency. Clear? Oscillators of the type VCO, which is what? Variable, voltage-controlled oscillators, they will what? They will tune that frequency. But still, you are generating how many frequencies? One frequency. Clear? Can you generate square volts? Anybody knows what we call these oscillators? Huh? I didn't hear you. I cannot hear you. A what? Oh, you forgot what it's called? Okay, but what I'm saying is that if you have taken the 477, you would know that it's called, for example, an astable multi-vibrator. Astable means what? Does not have a stable state. It will what? Switch from what? 1, 0, 1, 0, or 1 and minus 1, and so on and so forth. Sometimes you will generate what is known as a what? Ring oscillator. Ring oscillator. You will generate what? Pulses. Did you get my point or not? By the way, even the pulses that you are generating does not need to have a what? A 50% duty cycle. Did you get my point or not? Okay. Is it possible that you generate a sawtooth? What type of oscillator these? These are what is known as what? Sweeping oscillators. The one that you will do, that you use in your what? In your oscilloscope or in simulation in general, and so on and so forth. Clear? Different types of oscillator. Okay. Now, oscillators uses, this is a typo here. What does it use? Positive feedback. Positive feedback to produce an RF output at what? At omega naught, without the need of what? The input. Now, I need you to understand why did I change this one negative into what? Into positive. Let's look at a certain diagram, a circuit, so that you understand what I'm talking about. Details are yet to come. I'm just showing you the overview here. Let's assume I have this. Question, by the way. Question. What is this R? That's the load. What is this? That's a tank circuit. Do you follow me or not? Notice, by the way, at resonance, what is this one behaving? At resonance, it will behave as an open circuit, which means what? Which means the oscillation will go into the RF. Now, in here, what is this, by the way? What is this? This is, by the way, what is this? This is the VCC, but you do understand that when this one is what? When you sketch the AC equivalent, this one is what? Is the ground. Did you get my point or not? Okay. What is this? This one. What is this behaving as? That's the amplifier. Did you get this or not? That's the amplifier. Now, where is the input to the amplifier? We just said that we don't have any input to the oscillator. Yes? You need to take what? Part of the output. I want you to see what does this mean. And see if you can help me here. Okay. Now, let's assume this is N to 1. And let's assume the output voltage is V0. Can you tell me what is this? First of all, do you understand why did I take it from here? Why? I need you to understand. When I take it from here, it means if this voltage is positive, this is what? Negative. Now, you might say, then if it is negative, it means what? Negative feedback. Why did you scratch this to make it what? Positive feedback. You have to understand that this is a common emitter. And a common emitter introduces already a what? A 180-degree phase shift. So you are getting a what? A 180-degree, excuse me, 180-degree phase shift here, negative. With the negative becomes what? Positive. Did you understand? What do you mean becomes zero? You mean the phase zero? I thought you said zero. You follow me or not? Why? Because I want to pump more energy into the what? Into the output tank. Did you get my point or not? What is this? Can you tell me what is this? Minus V0 over what? N. Did you understand why did I divide by N? Because the coil here, by the way, this one, I'm using it at the transformer as part of what? As part, the primary, as part of the tank circuit. And the secondary is to provide for what? Feedback to the input of the amplifier. So what do you notice? This is an oscillator. What do you notice in the oscillator? It consists of two parts. It consists of an amplifier, and it consists of a what? A tank circuit. The feedback is a positive feedback. If this one is not a common emitter, let's assume that it's, or not, sorry, I said common emitter, it's common source. If it was not a common source, let's assume it was a what? A common gate, which does not introduce what? 180 degree. Then in here, where should I take it from? I should take it from up. Did you understand it or not? The feedback is negative or positive depending on what? Whether the amplifier is adding 180 degree phase shift of its own or not. The overall effect has to be a what? A positive feedback, not a negative feedback. The overall effect of the feedback plus the what? Plus the amplifier. Did you get my point or not? Yes or no? Okay, good. I will show you that feedback concept in just a second. Okay. So the oscillator uses positive feedback to produce an RF signal at the output at omega naught without the need of the input. Oscillators can also generate clocks. What does that mean? When I say oscillator generate clocks, the clock is a what? It's a square wave. By the way, that we will study later on in the semester. When I say later on means what? Next week. This is it. We have one more week. We will see how from what? From a certain reference oscillator, which is highly quality, we can design what? Dividing circuits to generate what? Clocks that are what? That are synchronized with the reference, which means it has the same what? It has the same characteristic, but at different what? Different frequencies. We will design dividers and multipliers and so on and so forth. We'll get to that next week. Oscillators can also be phase locked to a precise low noise, low frequency, a crystal oscillator. Crystal oscillators, these are the what? The highly reliable. Usually they are what? Of low frequencies, which means what? We need to what? Build up the frequencies from what? From the local oscillator. We synchronize with the local oscillator, but we need to what? We need to build it up. Did you get my point or not? Okay, let me just, premature, but just to get the idea, I want you to see this. This is premature. We'll get to it in detail. This is an oscillator, reference oscillator, generating a frequency. Highly what? Highly stable. You follow me or not? Now, where am I? This is, by the way, this is the PLL. PLL is the phase lock loop. This one is going to what? Is going to lock into this, which means what is the frequency here? The frequency here is the same as this frequency. So this one is the what? Is the reference frequency. If I put a divider in here, what does it mean? It means the frequency in here is what? Is M times this. And by controlling this divider, I can increase the output of the what? Output of the VCO at a frequency which is much higher than this one. Did you get my point or not? I can use this one for the RF application. Because oscillator usually, not oscillator, sorry, the crystal oscillators usually it's around what? Around 1 to 5 megahertz, which is not really a what? Which is not exactly an RF type range. Did you get this or not? But we could always build it up. And I will show you that next week. Okay, good. Let's continue. So oscillators can also be replaced by what? Synthesizer. What is a synthesizer? A synthesizer is an oscillator that generates a what? A range of frequencies rather than only what? One frequency. Are you following me or not? From the synthesizer itself, you can have what? Multiple outputs, each one at a different what? At a different frequency. Did you get this or not? Yes or no? Yes or no? That allows us to use synthesizers, the same synthesizer, both at the what? At the transmitter and at what? At the receiver, with the same shared hardware. It's the same shared hardware. We don't need two of them. And from one side, we synthesize what? Frequencies that are used for the up conversion. On the other side, we synthesize frequencies that are used for what? For the down conversion. Clear? Clear? Okay, good. Now, we will talk about all of these shortly in detail. Let's look, first of all, at a sinusoidal oscillator. How do you model it mathematically? A pure sinusoid is modeled as what? A cosine omega naught t plus what? Theta. Answer me the following question. Is the amplitude fixed? Is the amplitude fixed? Is omega fixed? And omega naught is fixed. Is the theta fixed? Theta is fixed. Everything is fixed. Do we agree? Agree? Okay. Notice, by the way, the phase always, when you look at the phase is always a parameter that is measured according to a reference. So when you say, for example, theta is 180 degree, you are comparing it with a reference of what? 0 degree. But the point that I'm trying to make is that what? Is this a function of time or is it fixed? It's fixed. It's not a function of time. Did you get my point or not? Okay. If you apply this to a spectrum analyzer means what? The frequency analyzer. What would you get? What kind of a spectrum would you get? You would get the following. Agree? All the power, by the way, contained in how many frequencies? One. What is the power? Can you tell me what is the average power? A square over 2. You follow me on that? What? It's a pure sinusoid. Does it depend on omega naught? Does it depend on theta? No. The amplitude, the power only depends on the amplitude. However, the problem is that we are not going to get a what? A clean oscillator generating this. What we are going to get is something like this. A plus some what? Fluctuations, which are also a function of what? T times what? Cosine omega naught t plus what? Some fluctuations of t. Notice, by the way, this has nothing to do with what? Modulation. Did you understand what I just said? Oh, no. This is what we are going to be referring it to as what? Phase noise. This, we are going to be calling it what? Amplitude noise. Clear? Amplitude noise or amplitude distortion. This is not crucial. Why is it not crucial? This one, the epsilon of t. Why is it not very crucial? Remember what I told you at the beginning, when you start the oscillation is just a what? Little bit, and then you begin to what? Amplify it. Are you following me or not? Eventually, the oscillator will what? Will settle on a what? Will settle on a certain level. You cannot go more than that level. And that level is determined by who? By the power supply, by the VDD. You follow me on that? So if there is a fluctuations in the amplitude, chances are these fluctuations will only last for a what? A short period of time. And then what? It reverts to the constant thing. This is not the crucial thing. Is this crucial? That's heavily crucial. Why is it heavily crucial, by the way? I want you to see something here. Okay, first of all, do you, before we continue, do you see the amplitude fluctuations here? Which one is the real one is the what? Sorry, the ideal one is the dotted line. Yes? And the solid one is the what? Is the fluctuation. Do we have a phase fluctuations? Do we have amplitude fluctuations? Both of them. It's not ideal. So if the parameter A, omega naught, and theta are constant, the spectrum is just an ideal impulse. But reality is that the amplitude and the phase are going to be what? Random. Resulting in what? Spreading the power. Instead of the power being concentrated in one frequency, it will spread and it will result in a what? It will result in a spectrum like this. And what does the spectrum look like? A spectrum look like a what? A long line, but that line suddenly what? It drops down as we what? As increase the omega. Did you get my point or not? Yes or no? This is the what? This is an IC. So the peak drops, same total. By the way, is it the same total power? It's the same total power, but instead of being what? Concentrated in what? Why, by the way, why is it the same total power? Assuming, by the way, assuming we neglect the amplitude fluctuation, why is it the same total power? Because the power does not depend on what? The phase. So if there is a phase fluctuation, this has nothing to do with the power. Power is still a square over 2. But instead of the power being what? Being concentrated in one frequency, it is now going to be what? It's going to be spread. Clear? Now, how do I measure this? I measure it through a parameter which is called what? L, J omega is a function of J omega. This will be measured in what? In dBc per what? Hertz. I want you to understand what is the C? It's with respect to the what? With respect to the carrier. dB, the degradation with respect to the carrier per unit what? Per unit hertz. Because why do I say per unit hertz? Depends on what? How far is it from the what? Center frequency. Did you get this or not? Now, what does effect have? What does this one have an effect? That phase noise. What does it affect? It affects the phase noise. The phase noise affect the following. Oh, sorry. Affect the following. Number one, sensitivity of receiver. Which means what? Increase bit error rate. Why? Can you tell me why? What does the oscillator has to do with the sensitivity of the receiver? First of all, do you remember how did we define sensitivity of the receiver? The sensitivity of receiver is the what? Is the minimum detectable what? Signal. The power, the weakest power that can be what? Detected. Why is this one going to cause? What is it going to what? Increase. He is, you mean reduce the SNR, not increase the NSR. Why? Because it is increasing the noise floor. Did you understand what I just said? Oh, no. The noise floor will what? Hence, signal to noise ratio goes what? Down. And if the signal to noise ratio goes down, the bit error rate goes what? Up. Second, selectivity. What is the difference between sensitivity and, this is not the same word. It might look the same word. This is sensitivity. This is what? Selectivity. What is selectivity of what? Of the channel, of the desired channel. Did you understand or not? The ability of the receiver to select the desired channel among what? Among other channels. Clear? How is that done? Let's understand this. This one is measured in terms of what? In terms of what is known as what? ACRR. A parameter that I don't want you to forget. What is ACRR stands for? ACRR stands for adjacent channel rejection ratio. The adjacent channel rejection ratio. I want you to see this. Before I give you an example, I want you to see this. This is the desired channel. Do you see this desired channel? This is what? An adjacent channel. By the way, before even we continue, what do you notice? You notice that the adjacent channel is stronger than what? Than the desired channel, because we are assuming that the adjacent channel is what? Is generated by a nearby transmitter. Clear? We are at the receiver. Yes? This is the local oscillator. This is the LO. This is supposed to be what? An impulse. And when you what? When you combine this with the desired channel, it is supposed to go to where? To the IF. Do we agree? But now let's see what we have here. I want you to see this is going to mix with this guy. You follow me or not? Generating this, the small one. This is going to be at the same distance as who? This guy. This guy. By the way, listen to me. Is this, when this one mixes with the local oscillator, the center, will it result in the same IF or IF displaced? You are not getting me. I need to explain to you a little bit carefully. What is this? In the middle, what is it? It's the IF. Yes? If you mix the interferer, this interference, if you mix it with the LO, not with the whole thing, just with the LO, where would you get? You would get this one. Did you get this or not? Which is of no what? No consequence or no danger to us. Why? Because it's not within the what? It's not within the IF. Did you get my point or not? However, I want you to see, if you mix this one with this one, the distance from here to here, by distance, I don't mean in what, in meters or kilometers. I mean in what, in hertz. Clear? The separation between this one and this one is the same as between this one and this one. Did you get this or not? Where will this one be? This one will be in the IF band, which is where? Show it to me here. Can you show it to me? This is this portion. Did you get my point or not? This is this portion. Where did this come from? It came from what? It came from mixing this with this portion here. Are you following or not? It's in the RF, in the IF branch. Yes? We need to figure out how much should this one drop down such that the effect of this interferer is what? Negligible. And let's see if you got my point. If you got my point, it means you should be able to answer me. How do I measure ACRR? ACRR is equal to C, which is the what? The desired power. Yes? Minus I. By the way, everything is in dB. Everything is dB. That's why my minus I. What is this I? That's in the interference power. Minus. Close the bracket. Sorry, close the bracket. Open the bracket. Bracket. Let's see if you can help me. L delta F plus what? B. Let me explain to you what this means. Okay. First of all, do you understand that everything is in dB? Why? Because I'm adding, subtracting. Yes? What is this one behaving? Why am I subtracting this? Because this one is aiding who? Is resulting in what? In increase the what? The noise level. Did you understand that or not? It's increasing the what? The interference power. Why am I, and by the way, am I adding this with this? If you factor out the minus, then it becomes what? I plus. Are you following or not? What is this? What is L delta F? L delta F is the what? Is the power spectral density of the what? Of the phase noise. PSD stands for what? Power spectral density. Yes? Cannot hear you. Or units, PSD. Watts per what? Hertz. When you multiply with hertz, remember this dB, when you multiply with hertz, which is the bandwidth, I'll explain that to you. Yes? What do you get? You get power. Did you get this or not? Okay, help me. The PSD of the phase noise at what? At delta F from what? Center frequency. Clear? Where is it in this diagram? Can you show me where is the delta F? Where is the delta F? Delta F is between what? This. Which means what is this? This is L delta F. Did you get my point or not? Yes or no? Okay. And what is this B? What bandwidth? Is it delta F or is it the desired bandwidth? That's the desired channel. This is the channel bandwidth. Clear? Okay, not sure. So let me give you some examples. Let me give you some examples so that you understand. This will be, by the way, in the final exam, in the quickie section. Quickie. Why is it quickies? You just need to know what to plug. Do you follow me or not? Clear? Okay. You don't want to talk about the exam. It's dreadful. So let's see if you can help me. Example. Suppose we have a GSM. GSM stands for what? The Global System for Mobile Communication. Receiver operating at 900 megahertz. 900 megahertz. Yes? The desired power, you remember how much is the channel? Say that again? 200 kilohertz. Over into the channel bandwidth. The channel bandwidth is what? 200 kilohertz. Clear? Okay. Now, the desired received power is, let's say, minus 100 dBm. Small or large? Small. Do we expect it to be large? Of course we expect it to be weak. Did you get this or not? Okay, minus the 100 dBm. There is an interferer at, let's say, minus 25 dBm. Stronger or weaker? Stronger. Stronger. Minus 25 dBm at delta F of what? Away from what? Desire. Which means what? The interferer is what, at what frequency? If this one is operating at what? 900 megahertz. This one is at what? 902 or what? 898. Did you get this or not? Okay. The spec desire or specifies an AC RR of 10 dB. The spec of the GSM says what? That the adjacent channel rejection ratio should be what? Should be 10 dB. What should the power spectral density of the phase noise be at what? B, i.e., what is L of what? 2 megahertz. Which means what? I want to see what is the level, this level. What is this level at what? 2 megahertz away from the what? From the local oscillator. Clear? Tell me, how do I do? ACRR, which is what? 10 equal to what? Minus 100 minus 25 minus L of what? 2 mega plus what? Tell me plus what? I know. What do I put here? 10 log what? 10 log 2 megahertz or 10 log 200 kilohertz? 10 log 200 kilohertz, not the 2 megahertz. Did you get this or not? Now, the 200 kilohertz is roughly what? 53. So this one is what? Is 53. Sorry, this one is equal to what? Is equal to 10 log 20 times what? Sorry, 200 times what? 10 to the 3. Clear? So what do I get? I get 10 equal to what? Minus 75 minus what? 53 minus what? L. Clear? Which means what? What does it imply? L of 2 megahertz has to be what? Roughly minus 138 dBc per what? Hertz. Did you get it? Did you get it? Okay, in other words, what does it mean? It means that this characteristic needs to drop below. In other words, if you take from here to here, it should be what? It should be minus 138 dB. With respect to the what? With respect to the carrier power. Did you get my point or not? Yes or no? Okay. Clear? Okay, good. You will see this calculation in the final exam as part of the cookie section. Okay. Let's get back to our discussion. Yes.
Is the answer DBMC or DBC?
No, it's with respect to the carrier. We are measuring always with respect to the carrier. It depends on what the carrier is. Sorry, with respect to the center frequency of the local oscillator. So whatever the local oscillator is the center frequency, this is with respect to it. Clear? Oh, clear? Okay, good. Now, this is what I was just telling you about. By the way, notice in here, if you plug in A, this is V naught of T, equal to what? A plus epsilon. This is what we refer to as epsilon. And this one is the phase noise. This is the amplitude noise. Okay. And you can rewrite this as what? A cosine. See, I need you to understand, where did this come from? This portion. Where did it come from? Okay. If you look at this, A plus A and cosine, A of T, cosine omega naught T plus B. If you neglect this, neglect it, what can you do? You can write this one as what? A cosine omega naught T, yes? And what is the second term? The second term will be what? Minus A phi and T plus what? A n of T sine omega naught T. Why? Because the cosine is a what? You lost me here? You lost me. Let me show it to you. What do I have? B naught of T equal to what? A plus A n of T cosine omega naught T plus what? Phi n of T. Can you write this in terms of the what? In terms of cosine size? So what do you have here? You would have what? A plus alpha n of T, or A, sorry, A n of T, times what? Cosine omega naught T, yes? Cosine what? Are you following me or not? Minus what? A plus what? A n of T sine phi n of T sine omega naught what? T. Did you get it? Yes or no? Now, let's assume that A alpha n is what? Is negligible. Negligible. Theta n, let's assume it's small. How do you approximate the cosine? 1. So what is the first term? A cosine omega naught T. What will this one result in? It result in this.
The time is
yes?
5 o'clock.
What was this one here? If phi n is a small, what do you approximate the sine with? Not by 0. By 0 it means what? There is no theta n. I say sine x. What is the sine x? Sine x, I cannot believe I'm doing this. X minus what? X cubed over what? 3 factorial plus x to the 5th over 5 factorial. If x is small, negligible, negligible, and you end up with what? With x. Which means what? This one will become what? A phi n of T times what? Sine omega naught T. But that's what? That's an AM modulation. Do you agree with me or not? The amplitude is modulated. That will explain what? That will explain this one. Clear? Clear? Okay, as opposed to what? As opposed to clean one like this. Clear so far? No response. What happened to page 5? Close page, here, page 1. So, clear this one? Okay, good. What is another problem of this that we saw earlier? In the mixer. In the mixer. Remember in the mixer when I told you that if you are going to generate what? If your oscillator is a what? Is a square wave, it will generate all types of what? All types of harmonics. And if this one is going to be what? Mixed with with the desired thing or something, the noise will begin to what? Will begin to fold. Remember the folding? It results in what? Increase of the what? Of the noise floor. That's what we meant by saying that it will affect both the sensitivity and the what? The selectivity. Clear? Okay, good. Now, before we get into this, and this is the feedback system. This is the feedback system. Again, by the way, I need you to understand one thing. When it says with negative feedback, it should be what? Should be positive, which means what? You need to understand that this one is going to provide for what? For another 180 degree. Clear? Let's not worry about this right now. Let's first of all understand. You don't need to write anything. Just follow the definition, which is what? Remember I told you, you can look at the oscillator as a what? As a negative resistor, or you could look at it as a what? As a feedback. Clear? In either cases, do we need an amplifier? We need an amplifier to sustain the oscillation. I want you to see this. Okay. We have a resonator or a tank circuit, and of course, an active device. Don't write anything here. Just download it. I will just post it. I want you to understand. What did I opted here? I opted for simplicity to take the tank as a what? As a series tank. Does the tank has to be parallel? Could it be a series tank? So this is the L, this is the C, but there is a what? There is an R in there, a parasitic in there. For this one to sustain oscillation, for this one to be what? Ideal, I need a device in which the input resistance in here will cancel what? R. Did you understand what I just said or not? Which means, what do I want RA to be? I want the RA to be what? Minus R. Because they will be in what? In series. Did you get this or not? So R with the minus R cancels, and you end up with a what? With a pure what? A pure L and C. Now you might say, oh, but who will sustain the oscillator? The amplifier. This is an active device. I just want to what? I just want this one to provide amplification, but it also providing what? A negative input resistance to cancel this R. Clear? Is this resistor real? Is this a resistor that I'm seeing in here? Is that a real resistor? That's not a real resistor that I can go to the lab and what? Put it there. There is no such thing as a what? As a negative resistor. Did you get this or not? This is the input where you have. So this is the equivalent circuit. The equivalent circuit is L, C, R, and RA. I'm equivalent circuit of this is just what? RA. This is the current. This is the voltage. Let's see if you can help me with the equation. Simple equation, all Kirchhoff's law. But the result is very clear that it will show you that this one will sustain, this one will provide for what? An oscillating effect. Any questions so far? Can we write the voltage law? What does the voltage tells me? It's a closed loop, the same current. It tells me that the voltage has to be what? 0. So, what is the voltage across the inductor? L di of t dt plus the voltage across the capacitor is what? 1 over C, the integral 0 to t, I of tau d tau. Tau is just a what? Dummy variable, so that you don't get confused with this. Yes? Plus what? R plus what? RA times what? I of t. The resistances are in series, they add up together. Clear? This equation 1. Take the derivative of this guy. So what do you get? L d second I of t dt square plus R plus RA di of t dt. Yes? Plus what? 1 over C derivative times the integral. Derivative of the integral is what? One cancel the other, and I end up with what? I of t. Clear? By the way, I'm assuming initial condition is equal to 0. I of 0 is equal to 0. Yes? Now, take the, did you understand this? Take the Laplace transform of both sides of this equation. The Laplace transform. Do you still remember the Laplace transform? No? No? Laplace transform? You must have. You must have. What is the Laplace transform of this guy? S square L, by the way, times what? I of S, but I'm putting the I of S here. S square L plus what? R plus R sub A times what? S plus what? 1 over C. The whole thing times what? I of S. Did you get this or not? Yes or no? This is Laplace transform. I cannot explain to you the Laplace transform. Guys, this is 301. 301. You took it like, I don't know, 5 years ago maybe. Clear? Okay. So, listen to me. This is equal to what? This is equal to 0. Could this one be equal to 0? I of S cannot be equal to 0. Which means what? It means this one must be equal to 0. This is what is referred to as what? The characteristic polynomial. So I equated equal to 0. What are the roots? The roots are what? Minus R plus RA minus B plus or minus B square minus 4AC. This C is not, is this capacitor. 4AC divided by what? 2A, which is 2A. Yes or no? I simplify it, I get this. Did you get this or not? Now, I want you to see something here. This is the imaginary part. This is the real part. Where do I want the pulse? Where do I want the pulse? If the system is to oscillate, I want the pulse to be located, a pulse of who? Of the closed loop transfer function or the characteristic polynomial. Yes? Where do I want it to be? I want it to be on the what? On the j omega axis, which means what? I don't want any real part. Did you understand? So, in general, let me show you one thing. If you do have e to the alpha t cosine omega naught t, how would you sketch this? You sketch this either through this. When is this? When alpha is greater than what? 0, yes? Or this. When what? Alpha is less than 0, that's a decaying, yes? Or what? When is this? When alpha is equal to what? 0. Did you get this or not? At the beginning, what do I want it to? At the oscillator, at the beginning, at startup, I want it to be like this. In the steady state, what do I want it to be? Third one. I definitely do not want it like this. Did you get this or not? This one means what? By the way, if I don't put that device, active device, then this one will be what happens. All the energy will begin to what? Will begin to be lost in R. Clear? This is the real part. Yes? At the beginning, what do I want? Can you tell me at the beginning, what do I want about R plus RA? Don't worry about the negative sign. R plus RA. What do I want it to be? 0 is what? At steady state. I don't want this term. So at a steady state, what is RA is supposed to be? Minus R. Do you agree? In the steady state, I want this term to be what? To be equal to 0. Did you get my point or not? Notice, by the way, if this term is equal to 0, what is this term equal? 0 also. Why? Because this is R plus RA. This one is what? R plus RA, the whole thing what? Square. If RA is equal to minus R, then this term is equal to 0. And what do I end up with? Where are the poles? The poles at plus or minus J, 1 over square root of what? LC. But what is that? That's the natural frequency. Did you understand what I just or not? That's the natural frequency. Is the poles are where? Are on the J omega axis. Yes? No response. Yes? And the oscillation is 1 over LC. But at the beginning, can you tell me what do I want R plus RA? Don't read, don't read. Don't read, you read. What do I want R plus RA to be? I want to be, my dear, if it is positive with this negative, it means what? The whole thing is what? Negative. The oscillation will what? Decay. I want to build it at the beginning. So what do I need? I need R plus what? RA to be what? Less than 0. So that this is negative. With the negative becomes what? Become positive. And the oscillation will begin to what? Grow. Yes or no? At the steady state, what do I want? At the steady state, what do I want? RA to be equal to what? Minus R. So that this one cancels, and I end up with what? I end up with the roots at what? At plus or minus J over 1 over at omega naught equal to 1 over square root of LC. Square root of LC, which is the what? Which is the resonance frequency. Clear? Clear? This is the first way. By the way, what did we analyze this system? In which domain? The analysis actually is done in the what? Sorry. It was done in the what? In the time domain model. This is in the time domain model. I started by writing equation in the time domain. Clear? Okay. But you can look at it differently as a feedback model in the frequency domain. Let's see if you can help. Any questions on the time domain? Yes or no? Did you understand the concept of a negative resistance? Okay, good. Now, we'll see the design of this one shortly. I just want to show you, first of all, the math. Okay, I want you to see now, this is the what? The oscillator analysis from a feedback point of view. We have what? We have a feedback, this. I want you first of all to see what is this feedback, positive or negative? Positive. What am I assuming this one? What phase is this one assuming that it introduces? I'm assuming that this one introduces a what? 0 degree. Why? Because if this one introduces negative 180 degree, then this one needs to be what? Minus. So that the net effect is what? Is positive. Did you get my point or not? Okay, good. Now, this is a closed loop positive feedback system. What does the G of S represent? In our circuit. In our circuit here. What is it? What is G of S? G of S represent the what? The gain, the amplifier. And what is H of S represent? H of S represent the what? The tank circuit. Did you get this or not? Yes or no? This one represents the tank circuit. I'm taking it from what? From the output of the tank circuit all the way feeding it to the what? To the input. Clear? This is misleading. Do you see this one? This is very misleading. Why is it very misleading? Because it gives the impression that there is a what? The input. What I'm saying is that this is internal effects, some noise, some distortion, some disturbances, the power supply or whatever. It's just to start things what? Going. It's just a triggering mechanism to let the oscillator start what? Start working. Did you get this or not? Okay, good. Now, what is the closed loop? Do not tell me you have not seen this before. This is, what is this? Where do you study this? In control classes or something. Yes? What is it? T of S. What is T of S? The closed loop transfer function. The closed loop transfer function, it's what? G of S over what? 1 minus G of S, H of S. G of S over 1 minus G of S, H of S. Now, let's see if you can help me. On the steady state, in the steady state, what do I want T of S to be? I want the T of S, the closed loop transfer function, to be equal to what? Equal to 1. Did you get my point or not? Equal to 1. But before that, in the startup, what do I want it to be? I want it to be greater than 1. To build up what? To build up the oscillation at the beginning. Okay. Clear so far? Okay. So let's continue. Everything is now in the frequency domain. There is no analysis here in the what? In the time domain. Everything in the frequency domain. So it's what? T of J omega. I replace S by what? J omega. Which means what? This one is called the what? The transfer function. What do I call this one? That's the frequency response of the overall system. The frequency response. Clear? T of J omega equal to what? G of J omega 1 minus G of J omega H of omega, which is equal to what? B of J omega V I J omega. Now, so what do I have? B of J omega equal to what? V I of J omega. By the way, is this small? Very small. Very small at the beginning, which means this one needs to be what? Very high. Did you get this or not? Yes or no? Okay, good. So it's V I of J omega, which is very small, times what? G of J omega 1 minus G of J omega H of J omega. What is G of J omega H of J omega is called? Open loop, the frequency response. Open loop, the frequency response. Why do they call it open loop? When you multiply G of J omega times H of J omega, it means you are opening the loop at what point? At this point. Not at this point, at this point. Did you get my point or not? Yes. Yes or no? I said at this point, and then I ask you, did you get my point? Okay. Did you get my point? It's G, if you do, listen to me. If you break this one, this loop here, then what do you have? You have G of J omega times what? H of J omega. Clear? Clear? Okay. So G of J omega, H of J omega is the open loop transfer function. Now, the loop gain, one more time, must be larger than 1 to ensure what? Startups, and then equal to 1 at what? At the steady state. Did you get this or not? At the steady state. Now, let's look at the conditions. These conditions, by the way, are called the what? The Barkhausen conditions, for the gentleman who came up with it. Clear? Okay. What is it? Absolute value. These are the magnitudes. Absolute value of G of J omega naught, absolute value of H of J omega naught has to be greater than 1 for what? Startups. And then what? For steady state, I would like what? I would like the absolute value of J of omega naught, absolute value of H of J omega naught equal to what? 1. Clear? Now, how about the phase condition? How about the phase condition? I want the phase of this guy plus the phase of this guy to be equal to what? Multiple of what? Integer multiple of what? Of 2 pi. Is that a positive feedback or a negative feedback? That's a positive feedback. Did you get this or not? It's 2n times what? Pi. Which means what? If you are using an inverting amplifier in G of j omega, if this is an inverting amplifier, then, for example, if you are using a common source, like the one I showed you, then what? The angle of h of j omega must also introduce a what? 180-degree phase shift. And that's what I showed you a moment ago, which I don't know where I put it. I have no idea where I put it. The one that, this one. This one. Did you get this or not? This one, you need to take it from here so that you get what? You get a negative phase. Not from here. Did you get my point or not? Yes? Okay, good. So, if you are using an inverting amplifier in G of j omega, for example, in the common source, then the angle of h of j omega must also introduce a what? A 180-degree phase shift. And vice versa. Vice versa means what? Vice versa means if you are using a non-inverting amplifier, then the tank circuit should also, the feedback should also be what? Non-inverting. Did you get this or not? Such that the net effect is what? The net effect is a multiple of what? Of 2 pi. This is the example that I just showed you. Clear? This is the example I showed you. There is no such thing as a what? As a passive oscillator. There must be amplification to start up the oscillation. Clear? To start up the oscillation. The final amplitude of the oscillation is, of course, limited by the what? IB boundary. Do you understand what IB boundary means? What IB? It's the current versus the what? The drain current versus the what? Versus the what? Versus the voltage. Are you following? When you sketch the load line, you know that the extension is what? The extension is to up to a certain value. That is going to sustain the what? Sorry, that is going to be the amplitude of your oscillation. Clear? By the way, the amplifier could be designed as a class A or class B or class what? C, even a class C that we talked about earlier. Are you following me or not? All of these can also be what? Can also be used in the design of the amplifier. And we'll see that shortly. This is what you get. What is this, by the way? Can you tell me what is this? That's the load line. Yes? And I'm biasing it here. This is the oscillation. I start with a slowly, big up. Once you reach the boundary, then it will what? It will what? It becomes constant. Clear? No response. Clear? Yes or no? Okay, good. Now, this is the equivalent circuit. Equivalent circuit of who? Equivalent circuit of this guy. Let's see if you can follow it. Equivalent circuit of this guy. Yes? Let's analyze. What do I have? I have the gate. This is the VGS. Yes? Then I have what? GM VGS from the drain. This is the drain to the source. Then I have the R. Then I have the what? The C. And then I have the what? The L. This is the tank circuit. Now, what is this C, by the way? Can you tell me what is this C? This C. Is it this C? Or is it with something else? I want you to see this. Where did this term come from? Can you explain this term? First of all, this CL is this CL. Yes? It is in parallel with what? CGS. Where is the CGS? The CGS is between the what? The gate and the source. Mapped back to what? To this port. Yes? Which becomes what? CGS over what? N square. Why is it over N square? Because that's an impedance. Did you understand that or not? Okay, so it's N square. This is the C. Can you tell me what is this R? What is this R? This R here. This R is the load resistance plus what? The input resistance of the what? Of the common source. The input resistance of the common source fed back N square. How come this one is N square? This one is divided by N square. This one is 1 over J omega C, whereas this one is just R. Did you get my point or not? Okay, good. So we have the following. the tank circuit, the impedance of the tank circuit, which is what? Which is this, is equal to what? SL. Can you explain to me where this came from? Where is the impedance of this guy? In other words, we are talking about what? We are talking about SL over what? S square LC plus what? SLR plus what? 1. Where did this come from? The impedance of this guy. Are you following me or not? This is parallel, which means what? It is 1 over R plus what? SC plus what? 1 over SL. Did you get this or not? You simplify it, this is what you get. Did you get my point? No response. Okay, what is the G of S? Remember the G of S. The G of S is this guy. Yes, it's the amplifier. What is G of S? G of S is V naught of S divided by what? Vn of S. Did you get this or not? This is for the amplifier. It's the output divided by what? The input. That's the transfer function of the amplifier. So what is it? It's minus Gm Z of what? S. If you replace this by Zs, if you replace this by what? Zs, then the V naught divided by the Vn is what? Is minus Gm times what? Zs. Because this VGS is the same as the input. Did you get this or not? Yes or no? Okay, so it's what? Minus Gm Zs. Gs times Hs is equal to what? Gm Zs over N. Where did this come from? Can you tell me where did this come from? Which is the open loop transfer function. Where did this come from? First of all, what happened to the minus sign? What happened to the minus sign? It happens, the minus sign is that because I took it from where? I took the feedback. 1 second. Where is the circuit? I took it from here. Yes? Which means what? This is minus. Yes? Where is this came from? This N. This N. This. Yes or no? So it's what? So it's what? Gs times Hs. This is G of S times what? H of S is what? Is Gm Zs over what? N, which is the open loop gain. Now, at resonance, what is Zs equal to? At resonance, what is Zs equal to? Zs equal to what? R. Which means what? At resonance, Gs, Hs equal to what? GMR over what? N. Which is the what? Which is the open loop gain at where? At resonance. Did you get this or not? Okay, good. What is the closed loop? The closed loop is what? G of S, 1 minus, divided by 1 minus G of S, H of S. If you plug in the G of S, this is the G of S, which is what? Minus Gm times this, and you divide it by what? 1 minus G of S, H of S, which is this, 1 minus this, and you simplify, this is what you get. This is what you get. Are you following me or not? Do you need to me to show you this, or can you handle it yourself? Did you lose me? Did you lose me? Prove this one. 1 point extra credit. Can you prove this at home? Should not take more than what? 2 minutes. Do it and then email me. Did you answer what I just said or not? 1 point. Go up from here. I want you to get to this. Did you understand it? Go from here. The G of S is this. The Zs is this guy. Yes or no? And the Gs, Hs is this. Plug this here. Plug this here. Where? Sorry. G of S is this guy. Plug it here and simplify. This is what you get. I want you now to tell me about the poles. This is what? These are the what? These are the roots. If they are the poles of H of T of S, it means they are the roots of what? The roots of the characteristic polynomial. This is what you get. Tell me now, what do I want? What do I want? Still waiting. Still waiting. At the steady state, what do I want the real part to be? No, not sorry, not at the steady state. At the startup. What do I want this to be? I want this one to be what? To be Negative. So that with this negative becomes what? So what does AL need to be? AL is the what? AL is the gain of the what? Of the open loop. Yes? What do I want the AL to be? Greater than 1 at the startup. Then at the steady state, what do I want AL to be? 1, so that this term is equal to what? 0. 0 plus or minus square root of what? Minus 4LC, which means what? J times what? Square root of LC. Yes? LC here. What happened to the 2 here? I lost you. There is a 4 here. Sorry. The 4 rescued me. There is a 4 in here. When you take the square root, it becomes what? 2. So it cancels with this, and you end up with what? Plus or minus J over what? 1 over LC, which means what? The frequency is what? Is this. Clear? Did we get exactly the same result as the negative resistance model? The negative resistance model, did we get the same result? We got the same result. Did you get this or not? Yes or no? Okay, so do this and email it to me. Deadline, some deadline. It's by tomorrow. By the way, you do know that I'm giving these 1 points as what? As freebie. And this one should not take you more than what? More than 2 minutes to do that. Clear? Oh, but you are going to clutter my email with it. Okay, when you send me an email in the subject matter, say the proof of the oscillator stuff. Now, let's continue. There is no way I will be able to finish this tonight, today. But let's start at least at the beginning. Now I want, after we learned the model, which is the what? Feedback model, or the what? Or the negative resistance model, I would like to be able to come up with a general design. You notice, by the way, I did not put a what? Components here. I left it in terms of what? Admittances. From the equations, we will see under what conditions will this circuit oscillate, and then I will choose what? I will choose those components accordingly. Did you get my point or not? In other words, this is a general derivation of the oscillator. A general derivation of the oscillator, and then we will take, I want you to see one thing before one second. I want you to see this. Just an example. This is one of the most widely used oscillators. It's called Collaptus oscillator. What do you notice? You notice there are what? C1 and C2, and there is an L here. I want you to see this, and I want you to see this. Does this one look like a C1, C2? This one will be the C1 and the C2, and this will be the what? The L. Did you get my point or not? So before we get into specific oscillators, let's understand the general design. Do you follow me or not? The general design, and then we can what? We can choose the components accordingly. Clear? Okay. So now, what do I have? I have a 3-port device. Why is it a 3-port? For example, if we are using a MOS, then it's a what? It's a gate, a drain, and what? And the source. Could I use this 1, 2, 4? Could I use them differently? This is just a model. Did you get this or not? Okay. So I have 1, 2, 4, and I put the 3 here. This is the 3. Clear? This is the 3. This port is 3. What is the small signal equivalent circuit of this one? Again, I'm representing everything in terms of Y, and you will see why in just a second. Because I'm going to use what? I'm going to use the current equation. And with the current equation, it's easier to deal with what? With the Y's. Are you following me or not? Yes? The Nortons, if you want to think about it. What do I have? I have the Y1. From 1 to 2, I have a what? Y1. Why is this Y1? YI. I'm sorry, YI. What is the YI represent? Input impedance. If this is a common source, then this one will be highly what? Capacitive. Do you remember this or not? Okay, but we will leave it this in general. This is just a generality. Then I have a GM. Why is it V1 minus V2? Why is this one multiplied by V1 by V2? If this is a common source, then this one should be what? VGS. And VGS is the voltage between 1 and what? So it's what? V1 minus V2. Yes or no? Or what is this? YO. YO is the output admittance. Yes? What is this? YL, which is the what? Which is the load. This is Y sub L. You cannot see the L here. Why the question? Okay. Y sub, what happened to the 5 minutes? Okay. Y sub L. This is the what? This is the load admittance. Are you following me or not? Notice, by the way, when I say admittance, that does not necessarily mean what? That it is a complex. Did you get my point or not? If it is real, then it will become what? Conductance. Did you get this or not? Okay. What is this, by the way? That's the P3. This one here is the third point, and this is the Y3. Did you get this? Yes or no? No response. Okay. Then what do? I apply the KCL. What is the KCL? Kirchhoff's current law at what nodes? At nodes 1, 2, 3, and 4. Are you following me or not? I apply Kirchhoff's current laws at points 1, 2, 3, and what? 4. I'm going to only show you one of them. I'm not going to go over this. That's what I did in my office, sitting there alone, did this. Let's see if you can help me with this. What is this? So I'm looking at point 1. At point 1. What is the current here? Sorry, here. What is the current? I have Y3, V1 minus V3, Y3 times what? V1 minus V3 gives me what? The current here. Yes or no? Okay. What is the second one? Y1 times V1 minus V2. What does that give me? Give me the current here. Did you get my point or not? Okay. This one. YI V1 minus V2. Where is that? That's this one. The current, this one. The current, this current, plus this current, plus this current has to be equal to what? Has to be equal to 0. Do you understand that or not? That's Kirchhoff's law. Clear? I do the same thing with what? With this node 2, node 3, node 4. Yes? And then I assemble them in a matrix format. In a matrix format, how many variables? 4 variables. Yes? How many equations? 4 equations. So I have what? A matrix B1, a vector B1, B2, B3, P4 equal to 0. And then I what? I have this matrix. Did you get this or not? Yes or no? And then I make some what? I make some assumptions, special cases. If a node is connected to the ground, if one of these nodes, 1, 2, 4, or what? 3, is connected to the ground, then the column and the row are what? Removed. Why? Because its value equal to what? 0. It's not going to contribute anything. Did you get this or not? Yes or no? If the what? If a node is connected to the ground, then the column of what? Column of what? Of this matrix. The entire column and the entire row will go what? I will put it equal to what? 0. Why? Because this point, a node in here will be equal to what? 0. So it doesn't matter what, when you multiply anything with 0, you get what? 0. Clear? Okay. For example, if B3 is 0, then remove the third column and the third row. If 2 nodes are connected, connected means what? The same point, then the corresponding row and columns of the matrix are what? Added together. Did you get my point or not? In other words, let's assume this point and this point are connected, which means what? This one is not there. Did you get this or not? This one and this one are connected. What do? The third column. The corresponding rows and columns of the matrix are what? Are added together. You add them together. Why? Because it's what? 2 points together. Did you get my point or not? Yes or no? Okay. I think I ran out of time. Did I run out of time? Okay, so let's take an example. The common source is what? B2 equal to 0. If I want common source, B2 equal to what? 0. Yes? So what do? I remove the second row and the second column. And what? 3 and 4. Where is the 3 and 4? Where is the 3 and 4? The 3 and 4 are what? Are attached together. Yes? Which means what? I add the what? I add the third column and the fourth column. When you simplify the matrix, this is what you get. Did you get my point or not? Now, this one cannot be equal to 0, which means what? This one, determinant of this one, has to be equal to what? Has to be equal to 0 to find the solution to this guy. Yes or no? Okay. So what do you get? You multiply this by this by this. You separate the what? The real part and the imagined part. You will get two conditions. Clear? Do I still have time or do I run out of time? Okay, next time we'll continue on this.